Hey, John here. Let's talk about some of the data types that are available in C, and the same ones are available in C++. All right? This is obviously the Wikipedia page on this topic. I'd rather show you the actual specification that talks about these, but that's got a copyright that I'm not allowed to rebroadcast. Blah, 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 blah. So Wikipedia it is, all right? I skimmed over this page. It seems perfectly reasonable for the subject that we want to deal with anyway. Specifically, I want to focus on integer data types. Okay? Scroll down here a little bit. You've got this table. In the C language, you've got a couple of different data types. You can see character, signed character, unsigned character, signed and unsigned shorts, and ints with signed and unsigned, and so on. Let's look a little bit about what this is and try to make sure that we know what we're talking about before we move on too far. A character is somewhat, formally defined as the smallest addressable unit that the machine can contain. And again, in a PC, Mac, cell phone, that kind of thing, it's going to be an 8-bit byte. Okay? Could be that you have a machine with bytes or words, whatever the smallest addressable unit is, that might actually not equal 8 bits. All right? And those are a little less common, but they definitely exist. So be careful. A character itself may be signed or unsigned. It really depends on the compiler, all right? And they mention that right here. If you want to know what kind of character you have, if you want to treat that 8-bit value as a signed integer type value, you have to tell it specifically, I want a signed character, or do I want to treat it as an unsigned integer value, okay? Just because the word char is sitting in here, or char as some people say, doesn't mean it has to be a printable character. These are just 8-bit integers, all right? Either a signed 8-bit number or an unsigned 8-bit number. Plain and simple. That's all that really means, okay? A short integer and an unsigned short, or shall I say a signed short and an unsigned short. This column over here, again, usually it's 16 bits, but look what the column says, minimum size. That's not the actual size, okay? It could be that a short on some machines is not 16 bits. Could be, 32. Could be 24. You don't really know. And that's the point, okay? How big is an integer? It suggests that a minimum integer is probably 16 bits. And there are a lot of machines that have 16-bit integers, all right? If you play around with these Arduino embedded processors and stuff, the integer on that thing, I'm pretty sure it's a 16-bit integer. If you want a 32-bit value on an Arduino, you have to ask for a long, okay? And integers come in both signed and unsigned types. On your PC, the integers are 32 bits in size. On your PC, a long, I believe, is also 32 bits in size. So these sizes over here that suggest this is the minimum preferred and recommended size of these data types are really all you got to work with when you're writing a C program. And it's really difficult to take a program that works fine on your PC and recompile it on an Arduino, because the Arduino and integer is all of a sudden a different size. So if you have a loop that counts up beyond, this range here, if it's signed, if you use a signed integer, or 65K on an unsigned integer, it won't work on an Arduino. It would on your PC with a 32-bit int. If you want to count up to 70,000 or something like that, all of a sudden it stops working. This is incredibly annoying to those of us who write programs that have to run on more than one kind of system. Or even on one system alone. How much space do you have? How big of a number can I put in an int on some machine? Who knows, right? That's the point here. The spec is somewhat vague because the C language was defined to be able to be modified and morphed and wrapped around, shall we say, any kind of a processor. Therefore, the language stays the same, but they change the meaning of some of the variables to suit the needs of the hardware. The point is, they did that because they wanted to allow the people that create the compilers to generate the best possible code for the specific kind of machine that they're trying to target. Okay? Now, that leads to what we call unportable code, like I said before. Now, this talks about some other types and things like that, but and you scroll down here and you finally get to this part right here. There's the focus of what I want to be talking about right now. Fixed width integer types. Or perhaps this section should have been called known width integer types, okay? So they talk about, whatever, a little bit of background here maybe, and the motive behind why we want stdint.h. If you're writing a C program. In C++, it is the same header file is called C standard int. Okay, for some reason, C++ language designers refuse to put a .h in their headers. Whatever, that's fine. That's a whole nother religious debate, I guess. So anyway, so you have these two different variations. It's interesting, of course, in C++ you can always pound includes a standard int.h, just the same as if you did this guy over here. But the other word, you can't do it the other way around if you have a C program. There would not necessarily be this header, okay? There's a little trivial question for you. I'm going to play a bar bet or something on that. Okay, so here we go. Exact width integer types get you over this problem. I want to write a program. I need an integer, and it's got to have 32 bits. How do I always know on any given machine that my variable will have the 32 bits it needs, or the 16, or the 8, or the 30, the however many bits it needs, right? 64-bit integer, and so on. So this header file here allows you to request a very specific width integer data type. It also allows you some other things, okay? Give me an integer that the compiler knows will be the fastest one for the CPU to use. Usually these would match the size, the number of bits that are in the registers inside the CPU, because that is the fastest type of data item that the CPU can manipulate, all right? So there's some variations in here that allow you to optimize your code in the way that you need it, and this allows you to write portable code, all right? It lets you know exactly what's going on. That's the key. So how does it work? Here's a little table down here. If you include that header file, you give this intn_t. This n is like, you put a number in there like 8, 16, 32, and so on. Now, it doesn't mean you can put an 11 in there or something. There are specific sizes, and they're going to be 8, 16, 32, okay? You can have an int 16_t. You can have a uint 16_t, and it does what is somewhat intuitively obvious, I would argue. An int 16_t is a signed integer with 16 bits, period. A uint 16_t would be an unsigned 16-bit integer, and the same thing for int 32 and so on, okay? There's some other ones in here as well. You want one with at least this many bits, but you're free to have more than that. And there's your fast one and so on. This guy here is kind of interesting as well. If you want an integer variable that has enough bits in it to hold the value of an address, like you're going to say, I have a variable called x, and I want to assign the address of, you got a pointer maybe that points somewhere in memory, and you want to store that pointer rather than in a pointer variable. You want to store it in an integer variable because you want to do some kind of an integer, manipulation on it for whatever reason. You do this sort of thing in operating systems all the time. Very low-level code. You need to be able to manipulate a pointer, not as a pointer, but as a number, as an integer. And they have a data type for that in here. That's what this thing is for, okay? All right, so given that little background, let's look at some code here. This is a C++ program. You can see me grabbing the usual IO stream and manipulators, and I grabbed the standard integer header file, okay? Now, I grabbed into my namespace these various things in order to make my code lines a little shorter. These were getting a little bit long. Normally, I don't do this, and quite often when I'm doing a lecture like this, I will put std:/hex down here. If you've seen any of my other videos, I usually use the fully specified names in here so that I never throw anybody off, okay? So I'm waving my arms here in the studio. Newsflash, when you see things like hex and cout, normally in my videos you would see std:/cout so that it is clear in no uncertain terms that I'm talking about the cout that is from the standard library, okay? In this case, though, I went ahead and grabbed them into my namespace. All right, so you can see these guys here. This is the key. So here's a function called dump. It has 4 arguments. Their types are signed 16-bit integer. So I call that one S16, so I can remember what it is. This one's an unsigned 16-bit integer. This one is a signed 32-bit integer. And there's an unsigned 32-bit integer. Okay? Now when I print all these out, I want to label them so I know what I'm looking at. Okay? I've got set fill on, so I got leading zeros so that the hex values have the right number of digits in them all the time, right? So a 16-bit integer, I'm going to print it out, 0x. I'm going to print a hex value with 4 digits because 16 bits is 4 hex digits, all right? Then I follow that with an open parenthesis, and I print the decimal value of that same variable, close parenthesis, and I end the line, okay? I do the same thing for the unsigned 16-bit value. I label it so I know what it is. I print out the hexadecimal value in 4 digits, and then I print out the decimal version of the same variable in parentheses. Signed 32-bit in hex and in decimal, unsigned 32-bit in hex and in decimal. All right? So anytime I call this, I do this to print out these 4 variables. So let's see how I use that. Here's a little teeny program. I've got 4 variables that match the same things that I'm going to pass them to the dump routine. Okay? And I got a signed, unsigned 16-bit, signed and unsigned 32-bit with the same names that you saw above. And I print a row of asterisks, and I put a little heading down here. I'm setting them all to 0. So I set all 4 of those variables to 0, and I call dump. Okay? Now down here, all this blue stuff is commented out. My editor makes them all blue. Pound if 0 means if false, and that says don't compile anything. That's in here, okay? And then my main routine ends. So all this program is going to do is print out this little heading, set these to 0, and call the dump routine to see what we've got. Looks like I already compiled it. Let's run prog1 and see what it does. Okay, there's the little heading, and you can see everything's set to 0, which makes sense. No tricks there. Signed 16-bit value for 0 in hex is all 4 digits of zeros. There's this guy, and so on for the other ones, all right? Now let's do something like this. Let's subtract 1 from each of those 4 variables and print them out again. All right, so they all start out as 0. It should make some sense that an assigned value that is currently set to 0, you subtract 1 from it, you should get -1. An unsigned 16-bit value, whose current value is 0, -1. Look what's going on in the hex over here, by the way. In both cases, 0 minus 1 in hex is exactly FFFF, all right? But in decimal, the unsigned variable, remember, it can't represent a negative number, therefore it has no assigned bit. All these ones together are, in fact, 65535, okay? Same situation happens with a 32-bit value. 32-bit value of 0, subtract 1 from it, no matter what it means to you and me, and this is a key thing here, regardless of what you and I might think, the CPU does the exact same thing, whether it's subtracting 1 from a signed variable or subtracting 1 from an unsigned variable. It doesn't matter. The mechanics of subtraction are the same. So in binary, you get the same value no matter what. It's your perspective that changes, okay? If the variable, the value of this 32-bit value is treated as an unsigned binary number, then the magnitude expressed in decimal is that. If this 32-bit number is a 2's complement signed binary number, then the value is expressed as -1. Simple, okay? Let's see what happens next. Let's go and add 1 to all those variables and dump it again. So here we go. Set them all to 0. Looks good. Subtract 1. We just saw that a moment ago. Add 1 and they're all back to 0 again. So there's 2 ways to think about this. On the one hand, if I add 1, or rather, if I subtract 1 from a variable, and then I turned around a second later and added 1 to it, it should end up where I started, right? That would be nice, okay? So 2's complement and unsigned numbers all provide that as a feature. At least they've done that for us, right? The weirdness comes in when you have this wraparound here. If you have an overflow situation or a truncation, you end up with a weird result. It's as simple as that. It wraps around to the other end of the spectrum of possible values that you can have, given the number of bits you got to work with, all right? And it goes both ways is the point here. If it goes from 0 to some giant number when you subtract, because you've truncated it, you can add, and you can then again truncate it and end up back at 0 again. Let's see what else I got going on in here. If we do this, what do? I say set all the bits except for the MSB to 1. The most significant bit is 0, and all the other ones are 1s. You can clearly see that. A 7 in binary is O followed by 3 1s, right? And an F is 4 1s and 4 1s. And so these are all 1s followed by 3 1s here, and the most significant bit is a 0. So in all cases, this is going to be, well, an assigned number. Those are going to be the biggest possible value you can have in a signed number, okay? Now, in a signed 16-bit 2's complement binary number, that value is 32767. It turns out it's the same thing in an unsigned number as well, right? Unsigned number doesn't have a signed bit, and it turns out even if it did, that most significant bit over here is a 0 anyway. So it turns out signed and unsigned variables have the exact same value until you exceed the maximum possible value that it can have, okay? And that works no matter how many you've got. 32-bit value, the biggest positive signed value is this, okay? With an unsigned variable, this is not the largest, but it is the same value as a signed variable has. This is only half as big as the maximum possible value you can get in a 32-bit number. In fact, up here is the maximum possible value you can get in a 32-bit number for 4 billion. And that 4 billion is basically the 4 gig, which if you're old enough, you might remember that used to be a limit on hard drive sizes. That used to be the maximum amount of memory you could have and so on. And now you know why. It's because it's the biggest number you can put in 32 bits. That's why we now use 64-bit computing, so we can have larger numbers of bits that representing bigger and bigger numbers. So, okay, fine. So we set that. We add 1 to that value now. Let's see what happens now. And, of course, weird things are going to happen. In this case, not to the unsigned variables, but to the signed variables, right? So look what's going on here. 7FFF. That is as many bits as you can have all on in the positive side for a signed 16-bit variable. If you add 1 to this, you can kind of do this in your head. If you can't, work it out on paper. Pause the video and write it all out longhand. If you set F plus 1, you get 0 with a carry, 0 with a carry, 0 with a carry. 7 plus 1 is 8. You can do that in hex. If you need to do it in binary, then write out all 16 bits. You're going to end up with all these, a whole bunch of 1s, and then you're going to add 1 to the least significant bit. The same thing will happen. You'll get all these carries, flipping all the bits to 0 in the sum, and then carrying it into the signed bit, causing a signed overflow, right? So this is the biggest unsigned positive number. You add 1, you end up with the biggest negative unsigned value, I should say, for 16-bit number is that number right there. And you can also play this game when you're looking at the even numbers and the odd numbers. The least significant bit is a 1 here, and you can clearly see that's an odd number. Least significant bit here is a 0, and both of these are even numbers. So again, all those little rules still apply. And it doesn't matter how many bits you have. If it's signed and you have a carry from the in the number that causes the signed bit to flip, and causes an overflow, you end up with a weird value, right? So you could take 2 billion plus 1 and end up with negative 2 billion in a signed number. And of course, in an unsigned number, you can just keep on going until you get up to the 4 gigs. Now, like we saw before, if you add 1 and then subtract 1, you should end up back where you started, and yes, you do. So here's me setting all the bits to 1 except for the MSB. You got all the 7 FFFFF. We add 1. In all cases, you can see there was a carry into the most significant bit with all the zeros on the rest, but all these values are different because of how we're interpreting them. Not because of what we did to the value, but because how we interpret them. So if you then subtract 1, you should get back to where you started, and yes, you do. These values match where we started here. So what is the takeaway in here? Well, if you need to know exactly how big your variables are, in terms of how many bytes they represent, you need to use standard int. Okay, it's as simple as that. You want a signed value, you get an int, with a number after it. You want an unsigned variable, you use the uint like this, okay? You want a 32-bit signed, use that. Don't say int. Use int32t if that's what you really want. If you want an unsigned one, use that, okay? With this in mind, we can now do math and get reproducible and predictable results. So thanks for watching. See you next time.